For decades, astronomers believed they understood Betelgeuse, a massive, dying red supergiant in the final chapter of its life, swelling with turbulent plasma and preparing for a titanic supernova explosion. But then it began behaving in ways no star of its kind should. It dimmed catastrophically in 2019, brightened unexpectedly, warped in shape, produced bizarre surface patterns, and even appeared to rotate at speeds that defied physics. Every new observation raised the same question: what is really happening inside this unstable giant? Today, we finally have an answer, and it's far stranger than anyone expected. Because Betelgeuse, it turns out, is not alone. Hidden in its enormous glow, nearly impossible to detect for over a century, is a companion star, a small, faint, gravitationally bound neighbor tugging at Betelgeuse's atmosphere, shaping its brightness cycles and distorting its outer layers. This single discovery may explain nearly everything scientists have struggled to understand about the universe's most unpredictable supergiant. I'm Alex from Universe Decoder, and today you'll learn the full story behind Betelgeuse's mysterious behavior, the evidence for its hidden companion, and what this means for the star's eventual supernova. First, imagine Betelgeuse as a colossal, unstable balloon of hot plasma, so enormous that if placed in our solar system, it would engulf every planet out to Jupiter. Inside, its core fuses heavier and heavier elements, causing the entire star to pulse and throb as convection cells the size of Earth's orbit rise and collapse. But the patterns astronomers observed didn't fit any known cycle of stellar physics. Betelgeuse wasn't just pulsing, it was wobbling. It wasn't just brightening, its entire shell was being tugged. Something external was influencing it. And that suspicion led researchers to analyze over 200 years of positional data. They found subtle, repeating movements, slight gravitational nudges that Betelgeuse could not be producing on its own. These nudges matched a cycle of about 6 years, far too long to be explained by internal pulsations. And when paired with the timing of Betelgeuse's dimming, brightening, and distorted surface, the pattern became undeniable. A companion star must be orbiting it. Weak, faint, nearly invisible, but powerful enough to reshape one of the biggest stars in our galactic neighborhood. Suddenly, Betelgeuse was no longer a chaotic mystery. It was part of a binary system. And that revelation would explain everything that comes next.
The idea of Betelgeuse having a companion star isn't new. Astronomers proposed it as far back as the early 1900s, but the evidence was always too faint, too noisy, and too easy to dismiss as surface turbulence. Betelgeuse's outer layers are so unstable, so violently chaotic, that even modern telescopes see only distortions and flickering hotspots. So for years, the binary hypothesis remained nothing more than speculation. But that changed dramatically after the Great Dimming of 2019. That event triggered a surge of global research. Nearly every major observatory turned its attention to Betelgeuse, gathering unprecedented data. Hubble detected heated material leaving the star, ALMA measured strange Doppler patterns, optical telescopes recorded asymmetric brightening, and a team at the Harvard-Smithsonian Center for Astrophysics noticed something no one else had caught. Betelgeuse wasn't just dimming, it was shifting slightly in position, almost like it was being pulled off-center. Meanwhile, another group at the Flatiron Institute in New York reanalyzed decades of radial velocity data. What they found was astonishing. Betelgeuse's motions weren't random. They followed a repeated wobble, a gravitational oscillation, perfectly consistent with a small companion star orbiting it roughly every 6 years. The star, now dubbed Beetle Buddy, is estimated to be about the mass of our Sun, but vastly dimmer, obscured by Betelgeuse's enormous brightness and turbulent outer layers. It orbits at a distance slightly less than the gap between the Sun and Saturn. And if it really exists, its gravitational influence explains almost every strange feature astronomers have documented for decades. Why Betelgeuse's brightening cycles fluctuate irregularly, why its shape shifts unevenly, why mass loss streams appear to flow in preferred directions, why the star's dimming events don't follow the usual physics of red supergiants. Even the mysterious 2,170-day brightness cycle suddenly fits perfectly, because it's not a pulsation, it's the orbital period. But one mystery remained, the apparent rotation. ALMA measurements suggested Betelgeuse was spinning so fast that according to physics, it should have torn itself apart long ago. That created a paradox. Either Betelgeuse was breaking the laws of angular momentum, or astronomers were misinterpreting something fundamental. And the truth was even more shocking.
When scientists combined the binary model with new high-resolution simulations of Betelgeuse's surface, everything clicked into place. Betelgeuse isn't rotating rapidly. Its surface is boiling so violently that it creates the illusion of rotation. The massive convection cells, rising and falling at speeds of tens of kilometers per second, generate Doppler shifts identical to those produced by a spinning star. And because Betelgeuse's surface appears blurry even to our most advanced telescopes, these turbulent bubbles blend together into what looks like a smooth rotational gradient. But in reality, Betelgeuse may be rotating far slower than initially believed. This discovery solves one of the biggest contradictions in stellar physics. A star of Betelgeuse's size simply cannot spin at the reported speed without violating angular momentum conservation. But if the rotation was merely a trick of turbulent plasma, then nothing is broken. The models make sense again. And the presence of a companion star makes the picture even clearer. As Betelgeuse orbits, its gravity warps the convection patterns, amplifying the turbulence on one hemisphere while suppressing it on the opposite side. This creates the uneven brightening, asymmetric hotspots, and unpredictable plasma arcs that astronomers have been trying to interpret for decades. It also explains the distorted shape of Betelgeuse. The star isn't perfectly spherical. It's stretched, uneven, and swollen in different directions. That asymmetry is exactly what we'd expect if a smaller star were orbiting nearby, pulling the outer layers toward it. The Great Dimming, once feared to be the onset of a supernova, also fits this narrative. Betelgeuse ejected a massive bubble of material, which cooled into dust and drifted directly into our line of sight. But the location of that ejection matches precisely where gravitational shear from Betelgeuse would be strongest. In other words, Betelgeuse may not be randomly shedding mass. It may be doing so because its companion star is actively disturbing it. A red supergiant on the brink of collapse is already unstable. Add a companion star tugging at its atmosphere, and you get a uniquely chaotic system. One that looks strange only because we didn't know the full story.
So what does all this mean for Betelgeuse's future? And for the long-awaited supernova? The discovery of a companion star doesn't mean Betelgeuse will explode sooner. In fact, it may mean the opposite. If Betelgeuse's brightness cycles and instabilities are caused by gravitational interactions rather than imminent core collapse, then scientists may have overestimated how close the star truly is to death. The core could still be tens of thousands of years away from collapsing, or it could be centuries. Or in a scenario some researchers cautiously entertain, it could indeed be sooner, but not because of surface behavior. According to modern models, the true sign of an imminent supernova would come from deep inside the core, not from the outer layers. Neutrinos, not dimming, would be the first signal. The surface would continue behaving chaotically right up until the moment of collapse. So, while the binary discovery solves many mysteries, it also resets the timeline. Betelgeuse might not be about to explode. It might simply be in a highly disturbed binary relationship. But one thing is certain. When Betelgeuse does finally go supernova, the event will be spectacular. From Earth, it will shine as bright as the full moon, visible even in daylight, casting shadows at noon, and lasting for weeks. But despite its drama, it will pose no threat to Earth. We are far outside the danger zone. Instead, humanity will witness one of the grandest cosmic events possible, a supernova unfolding in real time with every instrument we have pointed directly at it. And when that day comes, the existence of Betelgeuse will help scientists interpret the explosion better than any other supernova in modern history. Understanding this hidden companion gives us unprecedented insight into how massive stars live, interact, and die. Betelgeuse is no longer a chaotic puzzle. It is a binary giant shaped by forces we misunderstood for decades. And now that we finally know the truth, the universe looks a little clearer and a lot more extraordinary.